In this video, we're going to introduce the first new type of function and special type of function that we're going to work with in this part of our unit. That function is what's called the exponential function. Now, this is something you've maybe seen or read about in books or through the notes that you've covered in the course, but it's not a function we've done a lot, if any, work with so far. And that's got to do with the complexity that can come in with it. Now, an exponential function describes a function that is always of a certain type and a certain format. And that format is this. So f of x equals a to a power of x. Now, in this function, a is actually a constant, so just some number, and x is a functional variable. We've seen ones that look like x to a power of n, where x is our variable we're looking at and we're making our function dependent on, and n is just a constant. This reverts it and turns it the other way around. Any function that looks of this form is what we call an exponential function. And there's certain rules and a few names that we have to be involved with these. First thing we need to know is that x and a belong to a real set of numbers, i.e. they belong to any of the numbers that we exist. We also need to know that a is bigger than 0, so a can never be a negative value in an exponential function. It just doesn't work. As well as being bigger than 0, a also has a special name. A is what's called the base of the function. So it is the base which we depend and base our entire function on, essentially, hence the reason it's called that. And x is what's called the power, index, or exponent part of our function. I've seen all three names appear, so you need to know all three of them refer to the power, this bit up here. Now, this function is something that we can do a lot of work with. But the first thing we have to know is what the hell it means. What's the point of doing it? What's the point of looking at it? And what's the point of basing a function like this? And actually, it can be two different types of system that we have. Now, when we're graphing them, we always get two different forms. We always get a graph that either looks like this or a graph that either looks like this. Now, they're both the same form. Y equals a to a power of x. But the thing that changes in these is a. One that's of this form here, which is ever increasing, the value of a is bigger than 1. So the value that we choose for a is something that is greater than 1. So it's 2, 3, 6, 9, 10. And one of this, our value of a lies somewhere between 0 and 1. So a half, a quarter, a third. And what these two functions do is they allow us to model different systems and different behavior depending on what we're doing. This one here, always increasing and growing and tends off to infinity, we call this one the growth function. Okay, this one always allows us to model how something grows, how something develops, and how something increases. So this could be something like population of ants or bees within a system. This one here, because it always goes down and decreases and gets closer and closer to 0, this is what's called a decay function. So this tells us how something decays over time. So this could be something like the efficiency of a machine as it wears, or the effectiveness at using fuel of a car's engine over time as the mileage begins to build and build and build. This models those types of system. Now, when we're using graphs or drawing the graphs of these exponential functions without any form of transformation on them, there are a couple of key things we have to make sure we put every single time that we model. The first, and you'll notice it in both graphs, is that y is always bigger than 0. So the graph of both never ever goes into any negative values of y. Never crosses the x-axis at any point. As I said, if you do any transformations on the graphs, yes it could, but the original functions don't. The second thing is that if you're looking for where it intersects the y-axis, we know that x equals 0. So for our y-axis intercept, we know that x is equal to 0. So we know that y equals a to the power of 0. Think back to when we did indices back in National 5. Anything to the power of 0 equals 1. So regardless of whether it's a decay function or a growth function, whenever it cuts the y-axis, it always cuts at the value of 1. And another key point that we should always be able to mark on is when x is equal to 1. We should be able to get a coordinate along here when x is equal to 1 in both of these functions. Now, if x is equal to 1, y is equal to a to the power of x, so it's a to the power of 1, which is a. So that gives us the coordinate 1, comma a on the function. So that is another key point that we can mark on every single growth or decay function that we do and we use. We're able to say that for both of them. Whenever we're drawing these graphs and using them, these are the key bits of information we have to include, and these are the key things we have to remember. As I've said, if we do any form of graph transformation, we can then move the graph up and down, and maybe one or two of these will change, but in general, this is the way it always is and is always represented. Now, I've said we're going to look at why we cover exponential functions. We need to know what we can model with them, how we'd model it, and what it actually allows us to do. So let's look at an example for both a growth and a decay system and how it would be effective and useful. So let's imagine the otter population on an island increases by 16% per year. How many full years will it be until the population doubles? So this is something scientists could model when they're looking at animal population and species. Now, what you've got to do for something like this is model several key parts of the system, and the first thing you need to know is where you start. So in this case, we want to know what we're going to call U0, which we're going to call our initial population. Now, in this case, we don't know what the initial population is. We can still assume that U0 exists, but we know that that's what we're going to start with. And every year, we know that it increases by 16%. So at the end of every year, we're going to have that original 100% plus 16. So we're going to have 116% of the population every single year. So that means at the end of the first year, I'm going to have 1.16 times my initial population, because remember, 116% for this sort of thing, we can represent as the decimal 1.16. For my second year, I'm going to end up with the same. I'm going to end up with 1.16 times the previous year, U1. But U1 I can write in terms of my initial population. I can write it in terms of that. So I'm going to get 1.16 times 1.16 times U0, which gives me 1.16 squared times my initial population. My third year, I know I can write as 1.16 times my second year, U2, but I know U2 could be written in terms of the initial population in that. So I know it's going to be 1.16 times 1.16 squared U0, which then gives me 1.16 to the power of 3 U0. Now I can actually see a pattern starting to develop here. U1 was 1.16 times U0. Well, that's a 1.16 to the power of 1 hidden there. U2 was 1.16 squared U0. U3 was 1.16 cubed U0. So if I was to continue on here, I could determine that for any general year, UN, I could write this as a generic function of the form 1.16 to the power of n times my initial population U0. Think back to when we did increasing and decreasing amounts over several years back in National 5. It was always of the form a to a power of n times our initial condition. Well, this is very, very similar to that. We know that for UN equal to 1.16 to the n U0, that's my generic one for any year. Great, but the question was, after how many years does it increase and double? Well, what that means is at what point does UN become bigger than or equal to twice the initial population U0? i.e., when does 1.16 to the power of n U0 become bigger than or equal to 2U0? Which we can simplify to when does 1.16 to the power of n become bigger than or equal to 2? After how many full years does that happen? And at this point, it's just a case of trial. Okay, so we could say, right, so 1.16 squared, that equals 1.35 to 2 decimal places. That's less than 2, it's not doubled. After 3 years, 1.16 cubed, we know that equals 1.56, which again is still less than 2, so it's not doubled yet either. 1.16 to the power of 4, that's going to equal 1.81, which again is still less than 2. So we've not doubled our population yet. But in the 5th year, 1.16 to the power of 5, that equals 2.10, which is bigger than 2. So at this point, we've finally hit more than double our population. So what we can then say is that after 5 years, our population has doubled. The population has doubled. So after 5 full years, our population's finally hit that point where it's doubled. So just writing something in terms of the initial condition, even though we don't know that initial population, allows us to then use a method where we can just put in values and actually find a point where we know we're going to get to more than double. And it could be the same if it's a decay function. So let's imagine we have this one. A machine's effectiveness decreases by 5% each year. When it drops below 75%, it needs serviced. How many years until it needs serviced? So again, a question like this, we have to get our first initial condition. So let's imagine U0 is our initial efficiency. This will then allow me to say, right, so after the first year, I know it's going to drop by 5%, so I know it's going to be 100, take away the 5%, so it's going to be 95% effective each year, which is 0.95. So my U1 is going to equal 0.95 times my U0. It's going to be 0.95 times the U0. My second year is then going to continue this pattern on. It's going to be 0.95 times my U1, but again I can write U1 in terms of this. So I could say it's 0.95 times 0.95 U0, which is 0.95 squared U0. And I can then continue that on to my third year again as well. It's going to be 0.95 times my second year's efficiency. And I know my second year's efficiency in terms of U0 is equal to that. So it's 0.95 times 0.95 squared U0, which again is 0.95 cubed U0. And we can start to notice this same general pattern forming for this one. So I'm able to say that UN equals 0.95 to the power of n times my initial efficiency. I know that at this point, that is how I'm going to do it. What I also know is that when it's 75% and drops below that, that's when it needs service. So when it's at 0.75 times that initial efficiency, that's when it needs to be serviced. So I know that at this point, when that 0.95 to the power of n U0 is less than or equal to the 0.75 U0, that's when it needs its service. That's when it needs to be done. And again, at this point, I know that means when 0.95 to the n is less than or equal to 0.75. So it's now just a case of putting in the values. So if I said 0.95 to the power of 4, let's say, what that equals is 0.815. So it's still effective. If I then go to the next year, 0.95 to the power of 5, what I then get is 0.774. So it's still effective. It's not quite hit the 0.75 yet, but it's getting close. I then do the next year, my sixth year, 0.95 to the power of 6, and I get 0.735. Now that is less than the 0.75, so it's dropped below that 75% efficiency. So what I can then say is, therefore, after 6 years, it needs serviced. These exponential functions allow me to model these two systems, and that's what they allow us to do, is they allow us to look at these sorts of relationships, build up equations to represent them, and then use these to determine long-term effects and long-term goals that we're going to need. Exponential functions are quite important. This introduction was to give you an idea of how they are. We're going to look at a lot more to do with the rules and how we work with them in future videos.